Hello, welcome to Powerfully Simple 3D Machining Strategies with GibbsCAM. Now, that's quite a title, but I think that as we take a look at really just a handful of the over 40 individual 3-axis 3D finishing strategies that GibbsCAM offers, that you'll see that there's a lot of truth in the phrase powerfully simple, simply powerful. This presentation is being recorded, and you'll receive a link to the recording in an email tomorrow. If you have any questions during this presentation, you can type them into the chat on the right side of your screen. We have a team of GibbsCAM experts ready to answer your questions during the presentation. For the next half hour or so, we'll take a look at and compare a few of the more commonly used toolpaths from the three main families or groups of 3D strategies and techniques that GibbsCAM offers, and look at how they can reduce programming and machining time as well as improving surface finishes. And again, today we're limiting the presentation to toolpaths specifically in a 3-axis environment. We will look at using automated processes to further reduce programming time while simplifying the workflow and, if desired, standardizing strategies and techniques when you have multiple programmers. Standardizing the company's approach to programming can be a major step toward reducing setup times and minimizing mistakes at the machine, since everybody knows what to expect. As time allows, we'll touch on the toolpath factors that affect surface finishes. And beyond the two standard 3-axis toolpath engines, we'll take a look at how you could choose to utilize the multi-axis module to provide many additional toolpath styles that can be a tremendous benefit in a 3-axis environment. Additionally, using the multi-axis module on 3-axis machines can lay the groundwork for a possible future move into full 4 or 5-axis milling. GibbsCAM has three process types that support true 3D finishing: the surface process, the advanced 3D process, and the optional multi-axis process, each of which provide multiple options for defining and controlling toolpaths. Surface process toolpaths are the simplest, most basic 3D toolpaths in GibbsCAM. Although these have been enhanced significantly over the years, we can trace the lineage of these toolpaths back to the early 1990s GibbsCAM toolpaths that were actually the first toolpaths developed to test machining of solid models. There are three primary toolpath choices. The toolpaths are simple and straightforward and don't require a lot of input from the user. But in situations where they're appropriate, the surface processes are hard to beat as far as the simplicity of setting them up and the speed with which the toolpath is calculated. Advanced 3D processes offer us more than a dozen additional toolpaths, most of which can be used for finishing. The advanced 3D toolpaths not only give us more toolpath types and patterns to work with, they give us significantly more control over the details of how those toolpaths behave. 5-axis or multi-axis process toolpaths offer us a vast array of additional toolpath styles and patterns, which, though marketed for 5-axis, can output 3, 4, or 5-axis toolpaths and provide options and controls to precisely control all aspects of the toolpath. Additionally, the multi-axis module provides the ability to calculate various toolpaths based on different underlying technologies, such as a triangle mesh, which is the strategy most widely used in the industry, since the toolpath is a little simpler to calculate and it calculates a little more quickly. But toolpath can also be calculated based on the actual surfaces or based on a geodesic mesh, which tends to produce a smoother, more consistent toolpath. In order to show you the things that I need to show you in a reasonable amount of time, and to keep this presentation at least a little bit more interesting, I've built the toolpaths on this part ahead of time. However, in the interest of transparency, especially for anyone who may not be familiar with the fluid drag and drop method in which toolpath is created in GibbsCAM, I want to take one of the more complex toolpath elements on this part and create toolpath absolutely from scratch. Let's machine this feature here. And if I want to machine, I need a cutter. And I create a cutter simply by double-clicking on a tile on my tool list. I select the type of cutter. I'll take a ball mill, give it a diameter, 1/4 inch, make any adjustments I need to make to the length, and specify the number of flutes. I'll go with a 3 flute. Now the tools can be saved into tool list, and I can load individual tools or an entire tool list with just a couple of mouse clicks. To create the toolpath, I take the tool and drag it down to my process dialog, or my process tile list, and then select the type of toolpath I want to create. I'm going to go with a 5-axis. And here I can restore defaults. I can go to my tool button and set my speeds and feeds that I've saved for this tool, and then go to the Surface Paths tab. On the Surface Paths tab, I'll select the type of toolpath I want to create. I'm going to create toolpath based on surfaces, and I'm going to select a parallel to curve or curves. I select the drive surfaces I want to machine, and my edge curves, the curves that I want the toolpath to be parallel to. I'm going to select these and click OK. And I'm going to adjust my step over to 20 thousandths and go to my tool axis control page and make sure that I'm outputting 3-axis toolpath. Once I have everything set the way that I want it, I hit Do It to create the toolpath. Now if I want to create the same toolpath on other features, I could do that now. I can save this process if I like this and use it on other parts down the road, or I might want to machine multiple features with this same strategy. Maybe we want to machine this. Load the process back up, go to Surface Paths, include that in our drive surface definition, and include this in our edge curves. Recalculate the toolpath, and we could do all of these pockets at one time. At this point, I want to let you know that not all the toolpaths I'm going to show you are particularly good choices for the features that I have them machining. The point here is to show you that you don't have to settle when it comes to toolpath. You don't have to wish that you had more patterns to choose from. GibbsCAM provides you with a wealth of toolpath patterns to choose from, with a huge variety of ways to define and control those toolpaths. Yet they're easy to set up and calculate quickly. They're easy to modify, and once perfected, can be saved for use on other projects. Let's take a look at some toolpath. Now, this part's not terribly complex, and in reality, you could machine most of this, if not all of it, with just some simple linear toolpaths, such as lace cut from the surface process. But more than likely, you'd want to machine different areas of this with different strategies, both to improve cycle times by minimizing retracts, as well as selecting toolpaths that better conform to the shape of the area being machined, both to even further reduce cycle time and to improve effective surface finishes. This toolpath is from the surface process, and it's a simple surface lace cut toolpath. This creates a linear pattern at a designated angle to machine the selected face or faces. Lace cut is the surfacing toolpath with the most options and controls. It's also the only one that's designed to be used either for finishing or roughing. Lace cut is a true multi-face toolpath and can be set up very quickly. This toolpath is also from the surface process, and it's a surface flow cut, which is a single surface toolpath that's controlled by the ISO curves of the surface. This toolpath will automatically run parallel to either the U curve, which would be considered the short side, or parallel to the V curve, which would be considered the long side. With a couple of exceptions, it's not ideal for multiple faces since it will machine each face separately, but it's often hard to beat when you need just a quick toolpath to finish a single surface quickly and easily. On this toolpath, we're using the Advanced 3D Constant Step Over pattern. This toolpath is created by offsetting the boundary of the cut in a constant offset and maintaining the ridge height regardless of the surface angles. This last one is from the multi-axis process, and the pattern is parallel to curve or curves. This toolpath allows us to select one or more faces that we want to machine and curves that the toolpath will then run parallel to. Let's take a look and see how those look running. So we have the front two running different variations of a straight linear toolpath, and the back right an offset of the boundary of the faces. And then this one is running parallel to, in this case, just a single edge. Let's take a minute to focus on the center section now. This is an example of an area where the simple surface lace cut really isn't very well suited, and why it's important to have a very broad suite of toolpath choices at your fingertips. This toolpath is doing exactly what we asked, but due to the irregularities of the shape, this toolpath has to retract frequently to jump over areas that aren't part of the cut, but that are in line with the linear strokes of the toolpath. So while a linear lace cut is entirely appropriate for this toolpath, it's not one that we would choose for this toolpath. Let's look at a few toolpath choices that might do a better job for us on this. Now this one's an interesting option. This is an advanced 3D lace cut using the radial mode, which works in a fan shape from a defined center point. Since almost the entire feature here can be reached in unbroken lines from the center of the pocket, this toolpath works, and works quite well. However, since in this case the center point is located within the area being machined, the toolpath gets really dense toward the center point. So we end up with most of our toolpath with a much finer step over than what we specified, meaning the toolpath has more length. There's more toolpath required to finish this area. Now, using an advanced 3D constant step over toolpath, we achieve some very good toolpath. This one has a few retracts due to the way that offsetting of the boundary creates isolated areas as the offsets get separated from the rest of the shape. But this toolpath does a good job of following the shape of the area being cut. And with a finer step over, this would produce a very good finish in this area. This toolpath is less than a third of the length of the radial lace cut that we just looked at. Here's an advanced 3D in-curve flow, where the toolpath is morphing from the upper shape to the lower shape as it crosses the cut area. Now this is a very usable option and is getting close to what I would be looking for. But with this shape, as the drive curves change direction and head more toward the opposite drive curve, the toolpath gets really dense, which is less efficient and really not what I'm looking for. But this one only misses the constant step over by about 35 seconds in runtime. So it's still pretty efficient. But if we stick with the in-curve flow but slightly modify the drive curves, we can get this instead. This choice has the fewest retracts and is the fastest running of any of these choices. Now I do want to point out that there's nothing wrong with what I used to call playing what-if games. You can try multiple toolpath options in different areas very quickly and easily and kind of see what the effect is on your runtime. I used to do that frequently when I programmed every day. Moving on to some of the other features, this is an advanced 3D spiral lace cut. By defining the center of this arc as the center of the spiral, limiting the tool to the silhouette of the surfaces, and running the tool back and forth, we get a really nice toolpath that, somewhat flows with the shape and has minimal retracts. This one is using a basic raster lace cut, but from the advanced 3D process. So it's still that linear stroke toolpath, but this is from the advanced 3D. It has very few retracts, but really it doesn't flow very well with this shape. The shape's not straight, so straight line toolpath is not really going to flow with it. Here's an advanced 3D in constant step over pattern. This flows perfectly with the area to be cut and only has 2 retracts. This would work very nicely for this shape. And while we're looking at these, let's check out a few of the multi-axis or the 5-axis options for these features. Of course, all of these are set to output 3-axis toolpaths. This is a multi-axis toolpath based on surfaces, and the pattern is a morph between 2 curves. This is a beautiful toolpath that morphs from one edge to the opposite edge and gives me complete control over retracts. This is a multi-axis in geodesic mode, and the pattern is parallel to multiple curves with automatic detection of curves and default settings. So with automatic detection of curves, I don't have to define the curves. It selects them based on the surfaces being cut. This is going to be very similar, in this case, to a constant step over from the advanced 3D, but probably with a little bit better retract control. And this was just another multi-axis morphing toolpath. And then we get to this one. This is the multi-axis toolpath geodesic, based on geodesic or a geodesic mesh. And it's using the morph between 2 curves pattern. But it's similar to the other morph between 2 curves, but this is the geodesic version. This produces an incredibly nice toolpath for this shape that has no retracts and conforms to the area very well. This would probably be my choice for this area. Let's see what some of the toolpaths that I said I preferred look like in place with more realistic stepovers. My preferences are largely driven by a desire for few, if any, retracts, and a toolpath that, to my mind, flows with the major curves of the shape being cut. I started out finishing the outside vertical walls of the core with just a basic contour with Z-ramp turned on so it ramps down, and then following that up with an advanced 3D flats cut on the flange. Notice that the flats cut is avoiding the fixtures. This is a setting in the dialog, and you can specify how much distance there will be between the cutter and any fixture. Looking at the pocket on the front and on the back side, I started out with a multi-axis based on surfaces and selected a parallel to curves for the 2 pockets in the front. The difference is, for the first pocket, I only selected the back radius as the edge curve, and the toolpath looks like this. For the other pocket on the front, I simply added the side curve to the edge curve definition, and as a result, the toolpath starts here rather than over here, and works toward both these walls at the same time. We'll take a look at those 2 running. You can see that this toolpath is running parallel to only the back curve, while this one is running parallel to both the back curve and the side curve. For this one on the back side, I chose an advanced 3D in-curve flow. I extracted edges from the model and adjusted them slightly and ended up with this. This looks good, except to me the toolpath gets a little too dense for my taste over in this area. Now we could modify the curves and get most of that out, but just taking one shot at this is what I ended up with. For the one on the back left, I selected the parallel to curves based on a geodesic mesh. The same logic as the first 2, but based on a geodesic mesh rather than surfaces. You can see how smooth and consistent this toolpath is. And let's see those 2 running. This one is running nicely, but you can see that every stroke goes to that back right corner, making toolpath much more dense in that area. While this one is conforming to the closed sides of the pocket, and every step over is consistent. All right, for these H-shaped bosses, I selected morph between 2 curves for all 4 of these, but for the front 2, I used the option from the multi-axis geodesic toolpath. You can see there are few, if any, retracts. And for the back two, I use the option from the multi-axis surface-based toolpaths. These have a few extra tracks, but most of those could be tuned out with a few seconds on the linking tab. But I'm showing the toolpath with largely the default settings. And this is what they look like running. Each of these toolpaths is morphing from the long side to the short side, the geodesic toolpaths in the front and the surface-based toolpaths in the back. The geodesic patterns do make a cut to the outside of the short side before finishing so that the tool is climb milling at that edge rather than pushing the chip or burr to the outside. And in the back, you see that functionally a very similar toolpath is produced by the calculations based on surfaces morphed between two curves pattern. And with either, by setting appropriate cutting tolerances and stepovers, fitting arcs where appropriate, you can easily achieve the surface finishes your customers are looking for or produce a part that requires minimal polishing if that's the finish that you need. Moving on, for the 4 diamond-shaped bosses, I used a 2-curve flow from the multi-surface process for this one. I used a multi-axis based on surfaces morphed between 2 curves for this one. I used an advanced 3D in-curve flow for this one. And back to the multi-axis option for a geodesic-based morph between 2 curves for this one. You can see that all these options produce similar toolpath, but with varying numbers of retracts, although none of them have more than just a small handful. But they all start with one shape at one edge and morph as they move across the surface to the other edge. For this center section, I went back with the advanced 3D in-curve flow using that modified geometry. And then for the 8 pockets on the ends, I used the parallel to curve from the multi-axis toolpath based on surfaces toolpaths. And then I came back and added some toolpath for the blends on top of the bosses. Added toolpath to finish the floor-to-wall fillets. And if I hadn't finished these with the floors, I would come back and take care of these fillets. Now let's quickly run through the rest of this toolpath graphically. For this sample toolpath, we've used patterns from all 3 of the 3D modules: surface processes, advanced 3D processes, and multi-axis processes. Hopefully, I'm demonstrating that there are a huge number of toolpath choices in GibbsCAM for 3D finishing, and usually far more than one way to approach creating toolpath in a particular situation. Yet, these toolpaths are simple to set up, quick to calculate, and have the power to machine your parts your way. Now, once we've developed toolpaths, especially if they're well suited to the parts we commonly manufacture, it can be really helpful to save the processes. Let me load this one up again. This is an advanced 3D in-curve flow using a 1/4-inch ball mill and with a step over 20 thousandths. If I think, this did a really good job on this part, and I'm likely to use this strategy with the same tool on something else, I might want to save the process. Then I can call it up anytime I need it with just a couple of mouse clicks. I can simply right-click on the process, and this could be a multi-process for that matter, and save it to a folder and assign it a name that will allow me to know where to find it and know what it's going to do. If down the road I run into a situation where I think using an advanced 3D in-curve flow toolpath with a 1/4-inch ball mill will help me, I simply right-click on a process tile, hover over Load Process List, and navigate to the process I want to use. I'll grab this 001 Advanced 3D in-curve 1/4 inch ball mill with a 20,000 step over. I'll open up the process and select the surfaces that I want to machine. And then I'll define the drive curves that I want the toolpath to run parallel to. And then hit Do It. These saved processes capture the settings for the tool use, speeds and feeds, depth of cut, really all the information about the toolpath except specifically what to cut. And if the tool is not already in your tool list, the process will build it automatically. Over time, saving and utilizing these processes can really streamline your programming, as well as standardizing many of your processes to provide a greater degree of consistency from one job to the next, or for that matter, from one programmer to the next. I'd like you to see what using saved processes is like, so I'll program this part complete using saved processes. Here's the part that I had in my spare parts library, I call it. It's a 3D part. It is about 14 and a half inches long and 8 inches wide, a couple of inches thick. And the first thing that I like to do when I open up a model that I'm not terribly familiar with is to check it out a little bit. I'm going to open up my solid inquiry and my get draft angle. And with get draft angle active, I'm going to check the floors. These are flat floors, but these are 4.5 degree slope to these two floors. All right, now I want to check out the walls. These walls are 7.5 degrees, and these walls are straight. They are vertical. So of the 6 pockets, we have 4 that have flat floors and 7.5 degree walls. And we have 2 that have 4.5 degree sloped floors, but vertical walls. And close that too soon. And I also usually check a few radiuses just to see what I'm dealing with. These are 1-inch radiuses, and these are 504 and some change radiuses. All right, so I'm ready to start machining this. I'm going to open up my cutting tools and my cam, and I'm going to load a tool list in here. So I'm going to right click, go to load tools, and load my 3D finishing tools. All right, so the first thing that I want to do is rough this. So I'm going to right click, go to load process, 3-axis roughing, and load a volume mill 3D toolpath using a 1/2 inch rougher with a 40,000 step up. The step up in volume mill is what gives us definition to our 3D shape. It'll cut to the set depth per cut, but then when it hits the 3D surface, it'll just walk up that surface. It'll take passes higher and higher to give you a much closer to net shape cut. All right, and there we go. You can see it's putting as much definition to the 3D shape as it can within the bounds of the 30,000 step-ups that I specified. All right, so I'm going to clear this out and decide what I want to do next. I think the next thing I'm going to deal with is going to be the 7.5 degree walls on these 4 pockets. There are a few ways that I could approach that. The main thing that I want is minimal retracts, minimal pulls, times the tool pulls off the finished surface. So I want to start cutting this surface or this edge here and finish cutting this edge, but with a spiral down. So my passes are going to be closer together on the short side than on the long side. But let's see what we got. So I'm going to right click, go to load process list 3-axis, and I'm going to go to I want to go to my 5-axis engine again and go to surfaces, and I'm going to select this morph between two surfaces rather than the two curves. We looked at the two curves earlier. Let's look at a morph between two surfaces. We'll open that up and look at our Surface Paths tab. And we need to define our drive surfaces. So I'm just going to run around and grab these real quick. And then I'm going to do my edit surfaces. My first is where the toolpath is going to begin, which will be here. So my toolpath is going to begin at the intersection of this blue surface, my first edit surface, and the yellow. The yellow is what's being machined. And then the second edit surface is where my toolpath is going to end. And it's going to be the floors of these pockets. And then we'll say do it. And there's that toolpath. I'm fairly pleased with that. Blank tile, blank area of the screen, and let's deselect and decide what we want to do next. I think that I will machine the flats next. That's probably, well, that is definitely going to only be these floors here. But a part of many of my 3D toolpaths or my 3D parts is a flats cut, which automatically finds any flat horizontal surfaces and finishes them. So we're going to load processes. I'm going to go to Advanced 3D and grab this flats cut that uses a 1/2 inch end mill with a 10,000th corner radius. I'll select the entire part and do it. And that looks pretty good. All right, let's move on. What would I like to do next? I guess we could deal with these features here. We machine the walls and the floors here. I'll machine the walls and the floors here. So there are a number of ways that we could approach these walls. These are vertical. So we could do a contour, just a plain Jane geometric contour projecting the toolpath down onto this surface. But there's a better way if we have the 5-axis module available. So I'm going to right click and I'm going to go to load process, and we're going to go to the 5-axis and a swarf cut with an 1/8 inch ball mill. All right, I'm going to go to my Surface Paths tab and define my swarf surfaces, which are going to be these. And then get these over on this side as well. And those will be the swarf surfaces, the surfaces that we're actually cutting with the edge of the cutting tool. All right, and then I'm going to go ahead and define floor surfaces as well as those. And I will hit do it. And there's that toolpath. All right, continuing on. Now I guess I need to finish the floors. I'll do this surface here. Let me clear this out, right click. I think for this, I'm probably just going to do a basic lace cut. Well, I guess I'll do an advanced 3D lace cut. So I'm going to load process, 3-axis, advanced 3D, and grab a raster lace cut at 0 degrees. So on this side, at 0 degrees, the raster lace cut is going to start on the front and work its way to the back. So I'm going to do these separately because I want both of them to work from the outside in. If I did both of these at once, this one would work from the outside in, this one would work from the inside out, because it's going to, the direction of offset is going to be to the toward the rear. So let's go ahead and do that one. And that looks pretty good. We'll click on a blank tile. I'm going to click back here. And the only thing I have to do to machine that one is open this back up and change my cut angle from 0 to 180 degrees. Now it'll start on the back and work its way toward the front. And that looks good to me. So we finished the 4 pockets. We have finished the 2 pockets. We've roughed it. So I think next we will deal with the top surface here. Let's find something for that. I'm thinking probably a geodesic, maybe offset from multiple curves, and it should be able to pick those up automatically. So let's right click, and I'm pretty sure I've got one of those. So we're going to go to 5-axis, geodesic, and parallel to multiple curves, automatic with a, that's 1/2 inch end mill. That's not going to work. Let's go with a 1/2 inch ball mill. And then I want to open this up, and 50 thousandths is fine for a step over. Let's see. I think all the rest of that is good. And I'm going to hit do it. All right, and that looks good to me. We might could come back and try to work some of these retracts out, but it is moving a fair distance, so it probably does need to retract. And this is going to be similar to what we talked about on the constant step over cut. The way that the borders of this shape are being offset, you do end up, or you will end up, especially with a shape like this, with areas where the toolpath gets isolated, and so it has to retract to reposition to a new area. All right, so I think the last thing we have is this collar here. So let's select a process for that. I'm going to go back to the 5-axis, and we'll try geodesic, and I'm going to go 1/8 inch ball mill parallel to multiple curves, and this gives me the option of selecting the curve. So we'll try that as something a little bit different. All right, so we'll open this up, go to the Surface Paths tab, and define our machining surfaces as that one surface there. And we're going to go to, it's already set to user-defined curves, parallel to multiple curves, user-defined curves. I'm going to go to my guide curves, turn on my edges, and I'll zoom in a little bit because my eyes are not all that good. I'm going to select these edges here as the edges that we want the toolpath to run parallel to. And let's say do it. And there's that toolpath. That calculated real fast. All right, let's see what that looks like. If we start from a rectangular block and let this toolpath do its thing. Well, hopefully I've shown you that GibbsCAM has a wealth of 3D toolpaths and capabilities, far more than could be addressed in a short presentation. We've barely scratched the surface, but hopefully you've seen that there are tools here that, while simple to use, can powerfully tackle even your most demanding 3D toolpath needs. If you'd like to see more or dive deeper into how GibbsCAM can reduce your programming costs while providing the very best surface finishes for your customers, give your local reseller a call and schedule a personal and personalized demonstration. Once again, a link to the recording of this presentation will be sent out tomorrow if you'd like to watch it again, or you could share it with a colleague. Thanks again for attending, and have a great day.